What does before even mean if time had not yet begun? If the universe started 13.8 billion years ago, what was there 1 second earlier? Was there a silent void? Empty space? But if time itself began with the universe, then before may not exist at all. The Big Bang is often described as the beginning of everything, but everything includes time. And if time was born in that event, then asking what came before, it may be like asking what lies north of the North Pole. Did nothing exist before the Big Bang? Or are we using a word that physics does not even recognize? And if nothing is impossible, what does that say about reality itself? If you enjoy exploring questions like this, where physics meets philosophy at the edge of the known universe, consider subscribing. And if you find this video valuable, a like helps more people discover it. The Big Bang wasn't an explosion. The Big Bang was not a bomb exploding into empty space. It was not matter flying outward into a dark void. The idea comes from Albert Einstein's theory of general relativity, published in 1915, which showed that space and time form a flexible structure called spacetime. That structure can stretch. In 1922, Russian physicist Alexander Friedmann solved Einstein's equations and found that the universe could expand. In 1927, Belgian priest and physicist Georges Lemaitre proposed that everything began from what he called a primeval atom. Then in 1929, Edwin Hubble, working at Mount Wilson Observatory in California, observed that distant galaxies were moving away from us. The farther they were, the faster they receded. This relationship, now known as Hubble's law, revealed something profound. Space itself is expanding. Galaxies are not racing across a fixed stage. The stage itself is growing. If you rewind that expansion, everything converges toward a hot, dense origin. Rewind far enough, and the math predicts a singularity, a point of infinite density and temperature. Infinity is usually a sign that our equations have broken down. Is the singularity a real beginning, or a limit to our understanding? When time itself begins, we tend to treat time like a steady river. Seconds pass, hours flow. But in Einstein's universe, time is not separate from space. It is woven into the same fabric. Together they form space-time. If space-time began expanding 13.8 billion years ago, then time may not stretch backward beyond that point. In general relativity, the Big Bang is not only the birth of matter, it is the origin of the cosmic clock. The earliest moment physics can describe is the Planck time, about 10 to the power of minus 43 seconds after the beginning. A decimal point followed by 42 zeros, and then a 1. Before that instant, our current laws fail. Stephen Hawking compared this to geography. Asking what came before the Big Bang may be like asking what lies south of the South Pole. The question itself loses meaning. There may be no earlier. What scientists mean by nothing? The word nothing sounds simple. In everyday life, it means emptiness, a blank room, a vacuum. But in physics, even empty space is not truly empty. Quantum field theory, developed in the 20th century by scientists such as Paul Dirac and Richard Feynman, describes reality as fields spread across space. Even in a perfect vacuum, those fields fluctuate, they vibrate. Because of the Heisenberg uncertainty principle, energy can briefly appear and vanish. These fluctuations produce virtual particles. They flicker into existence and disappear almost instantly. Experiments at places like CERN confirm that the vacuum is alive with activity. So when physicists say nothing, they rarely mean absolute non-existence. They usually mean a quantum vacuum, no particles, but still governed by physical laws. Not nothing. Something deeply strange. Has absolute nothing ever existed at all? Or is it an idea that works in language, but not in physics? At this point, it might seem like physics has answered the question, but it hasn't. The quantum beginning. As we approach the universe's origin, gravity becomes extreme. At those scales, Einstein's smooth spacetime must obey quantum rules. But general relativity and quantum mechanics do not fit together easily. This clash is one of the deepest problems in modern science. Physicists like John Wheeler proposed that at very tiny scales, spacetime itself may be turbulent. He called this quantum foam. Instead of a smooth surface, reality at the smallest level could resemble a restless sea. In the 1980s, Stephen Hawking and James Hartler introduced the no boundary proposal. In their model, the universe does not begin at a sharp edge. Near the origin, time behaves more like a spatial dimension. Instead of a starting point, there is a smooth rounding, similar to the surface of a sphere. Imagine travelling north on Earth. Eventually, you reach the North Pole. There is no boundary, no cliff. Just a place where directions lose meaning. Hawking suggested the beginning of the universe might work the same way. If so, the Big Bang was not a moment when something emerged from nothing. It was a transition. But a transition from what? The inflation twist. In 1980, American physicist Alan Guth proposed a radical addition: cosmic inflation. According to this idea, the universe underwent an extremely rapid expansion about 10 to the power of minus 36 seconds after the beginning. In a tiny fraction of a second, space expanded faster than the speed of light. Inflation explains several mysteries. It accounts for the remarkable uniformity of the cosmic microwave background radiation, first detected accidentally in 1964 by Arno Penzias and Robert Wilson at Bell Labs. It also explains why the universe appears geometrically flat. But inflation changes the stakes. Some models suggest it could begin spontaneously within a quantum vacuum. A tiny fluctuation could inflate into an entire universe. Our cosmos may be the result of a quantum event, yet that vacuum would still exist within some broader framework. Physical laws would still operate. Fields would still fluctuate. That is not nothing. It is structure. Either the universe emerged from a quantum state governed by laws, or it marked the creation of those laws themselves. And if the laws did not exist before, how could anything happen at all? The problem with before. The word before assumes time flows smoothly backwards, like a film you can rewind. But several modern theories suggest time may not be fundamental. It might emerge from deeper physics. In thermodynamics, time has direction because of entropy. The second law, formulated in the 19th century by Rudolf Clausius and Lord Kelvin, states that entropy tends to increase. Disorder grows. That increase defines the arrow of time. We remember the past because it was more ordered. Near the Big Bang, entropy was extraordinarily low. That special condition remains unexplained. Why did the universe begin in such an ordered state? Roger Penrose has argued that this low entropy beginning is one of cosmology's deepest puzzles. If time's direction depends on entropy, then before the Big Bang may not mean what we think. Without changing entropy, there may be no meaningful distinction between earlier and later. No ticking, no sequence, just a boundary where familiar concepts lose structure. The bounce hypothesis. Not all physicists accept a true beginning. Some propose that the Big Bang was not a creation event, but a transition. Loop quantum cosmology, developed by researchers such as Abhay Ashtekar and Martin Bojewald, suggests that gravity becomes repulsive at extremely high densities. Instead of collapsing into a singularity, a previous universe might compress to a tiny size and then rebound, a big bounce instead of a big bang. In this view, our expanding universe was once contracting. The singularity disappears. The breakdown in Einstein's equations is replaced by quantum corrections. Time continues smoothly through the bounce. There are other cyclical models. Roger Penrose's conformal cyclic cosmology proposes that the remote future of one universe becomes the beginning of another. No absolute start, only endless transitions between cosmic aeons. But if a previous universe existed, why can't we see evidence of it? Scientists search for subtle patterns in the cosmic microwave background, hoping to detect traces of a pre-Big Bang phase. So far, no clear signal has been confirmed. If the bounce idea is correct, then nothing never existed. There was always something, just a universe in a different state. Multiverse speculation. Inflation introduces another possibility. In some versions of eternal inflation, proposed by physicists such as Andre Linde, expansion never fully stops. Space keeps inflating in some regions, while bubble universes form within it. Our Big Bang would then be one local event inside a much larger multiverse. Each bubble could have different physical constants, different particle masses, even different laws. In that picture, asking what existed before our universe may be like asking what lies beyond our cosmic horizon. The answer could be more universes, an enormous landscape of possibilities. But caution is essential. The multiverse remains theoretical. No telescope has detected another universe. No experiment has confirmed their existence. The idea arises from mathematical extensions of inflation and string theory. Still, it shifts the question. If a broader structure existed, then our universe did not emerge from nothing. It emerged from something larger. The energy question. There is one more surprising idea. In the 1970s, Edward Tryon proposed that the total energy of the universe might be zero. Matter carries positive energy. Gravity carries negative energy. If these balance perfectly, the net total could equal zero. The universe would not violate conservation laws by appearing a zero-sum system. This does not mean it came from philosophical nothing. It means the equations allow a universe whose total energy cancels out. Alexander Vilenkin later suggested a universe could tunnel into existence through quantum mechanics, much like particles tunnel through barriers in laboratory experiments. But again, this requires a quantum framework and physical laws. Zero energy is not non-existence, it is balance. The real frontier. We can observe the universe back to about 380,000 years after its beginning through the cosmic microwave background, mapped in detail by satellites like COBE, WMAP, and Planck. We can model earlier moments using particle physics tested at CERN's Large Hadron Collider. We can describe nucleosynthesis, inflation, and quantum fluctuations with precision. But there is a limit. Beyond the Planck time, we do not yet have a complete theory of quantum gravity. Our equations stop. Our measurements cannot reach further. This boundary is not a wall in space. It is a boundary in knowledge. When we say nothing before the Big Bang, we may simply mean our theories cannot extend beyond that point. The absence is not physical, it is informational, and that distinction matters. So did nothing exist before the Big Bang? Modern physics does not confirm absolute nothing. It describes a hot, dense origin. It models quantum fields. It explores bounces, cycles, and inflationary landscapes. It even allows a zero-energy universe. But none of these models describe non-existence. They describe structures, laws, fluctuations, transitions. Perhaps the greater surprise is this: the concept of nothing may not be physically meaningful. It may be a word shaped by human intuition rather than mathematics. The Big Bang may mark the beginning of our observable history. It may mark the birth of spacetime itself, or it may be one phase in a larger pattern we barely glimpse. What lies beyond that boundary remains unknown. And perhaps the most honest answer is not that nothing existed, but that we are still learning what existence truly means.